Hello everyone. My name is Sergio Lopez, and I work as a software engineer in the automotive team at Red Hat. I think we should probably start already because we have a lot of things to say and not much time. So in this talk, I'm going to try to explain a little bit about the specifics and the particularities of the automotive industry when it comes to virtualization. And I'm also going to talk about the work we've been doing over the last year and the last couple of years to get QEMU ready for the challenges that the automotive industry presents for us. Now, to properly address this matter, we need first to answer two questions. The first one is, why would a car need any form of virtualization at all? Because if you are familiar with cars, they are usually driven by microcontrollers. They are also driven by kind of embedded systems. So it seems quite the leap to go from embedded systems all the way to something that actually requires virtualization at all. And the other question is, how is the automotive industry different from any other industries that are already using virtualization? And to start thinking about that, we need to learn just a little bit about the automotive industry itself and the evolution, and the fact that the automotive industry right now is going through a transition period. This is kind of a simplification, but it's just to give you an idea that originally cars mostly look something like this. And MCU is just a fancy acronym for a microcontroller in the automotive industry. And basically, originally cars had a bunch of microcontrollers all around the car, mostly independent. If they are connected, they are only connected to a CAN bus, usually just for logging to events to some kind of central console. But for the most part, it's something that is completely independent. A completely independent devices managing local peripherals that are directly connected to them. In this design, there is a design that works. It has worked for many years, but the problem it has is that it's completely static. The moment the car gets out of the factory, there is no way to alter the behavior of the car, except by physically replacing cars or changing the wiring. And now, another problem with this approach is that the fact that it's so inflexible means that if you have a single automotive platform that you are sharing with multiple models, which is something that the car manufacturers like to do, of course. If you have different models, you need to actually rewire and replace physically those components to be able to offer different experience with different models. And that's probably one of the main reasons why the industry evolved to something like this. In this design, those MCUs, those microcontrollers have been mostly replaced for endpoints. There are sensors, they may be mechatronics, and those sensors and mechatronics are connected to something called electronic control unit or ECUs. ECUs are more complex computing devices than MCUs. They may have firmware, they may have more power, and they basically receive and send events to the sensors, and they may or may not be connected between them. So this is a more flexible approach. You can actually change the behavior of your car by changing just the ECUs or by changing the firmware on the ECUs. But it's more flexible, but it's still relatively static. In this design, you may also have what is called an in-vehicle infotainment system, or AVI. But this is still kind of isolated from the rest of the car. It's something that is there. It's kind of an evolution of the original car stereo. It may show some of the vehicle information, but it's, for the most part, isolated. And from this design, the industry is moving towards to this one. In this one, the ECUs have become some proxies. So it's roughly the same hardware, but the behavior has been moved from the ECUs to something that is called the central control unit. Now, this central control unit is something closer. It's more powerful computing in computing terms. It may have real-time cores. It may have application cores. It may have a GPU. It may have hardware coding and decoders. So it's something closer to what we maybe used to see in laptops, in PCs, in servers. And it's in this design, the CCU is becoming, well, the sensors and the mechatronics are becoming mostly peripherals to the CCU. So this is basically a computer, and everything that's around the car is basically a peripheral of that computing, communicating through the sound proxies. All the behavior, or most of the behavior, is implemented in the CCU itself. And optionally, the IBI can also be running in the CCU. This is optional, but since you have enough compute power, you can choose to also drive your IBI directly from this single board computer. Now, this is something that comes with a number of benefits. For instance, what we have here is mostly a microcontroller-driven design. This was mostly a firmware-driven design or firmware-driven car, and this is mostly a software-driven car. This is something that not everything, but many behaviors of this car can be updated or changed by replacing software components. This comes with a number of advantages. So for instance, you can deploy more complex systems. Many of those cars are actually connected all the time to the internet to offer remote services. So you can check your car battery level, or start up the car remotely, or set up the air conditioning system from your home before going to your car. And also comes with the advantage that you can have OTA updates. You can, if there is a bug in your car, it can be updated eventually by issuing some update the same way you will update a phone or a laptop. Also, for car manufacturers, this also means comes with the advantage that a single platform can easily be used on different car models without having to actually physically replace components if you don't want to. Because you can simply change the behavior of the software, install different software components or replace them, and you will be changing the behavior of the car. This is the reason why most of the industry is going in this direction. Some of the car manufacturers are already there. Some are going in that direction, and they will eventually get in the following years. Now, there are various reasons for going in this direction, but the main one is the ability to have something closer to what is being coined as a software-defined vehicle. Now, before jumping into the topic of in virtualization itself, we need to talk just a little bit about functional safety, which is not the most fun topic to talk about, but we need to at least acquire and clarify some of the terminology, because we are going to see it just in a minute. And basically, from a high-level view, the FUSA is an industry standard that basically allows you to analyze and classify the risks in the different components of a car. It's usually referred as electronic and electrical components, but it also includes the software. The main advantage of this, well, one of the main advantages is that it provides a common language for different companies to collaborate, because usually a single company, a single car is not built by a single company. You are sourcing parts from different other partners. So you need to actually be able to ask them and establish the safety requirements using a common language. To classify the risk, there are various factors that are factoring, but the main ones are the potential harm to individuals if the component fails, and how sensitive is to timing. And the classification goes from ASIL A, which is the lowest criticality, to ASIL D, which is the highest one. And there is also another classification, which is QM, where no requirements directly apply. Now, the best example, or the one that is used to illustrate this classification, is that an electronic brake system, or EBS, is going to be ASIL D, because the potential harm to individuals is very high. If the brakes doesn't work, it's usually very bad. And the time sensitivity is also very high, because you need to apply brakes potentially in a timely manner. On the other side of the spectrum, as a quality managed component, you can think usually about the ABI, the infotainment system. If you cannot listen to Spotify during your trip, it may be more boring, but it's usually not dangerous to your life. So, okay, so knowing that the industry is going in the direction of consolidating hardware and knowing a little bit about functional safety, we can also understand how the most straightforward approach to virtualization in the automotive industry is by simply having a hypervisor and then taking the behavior that was in the ECUs and put it in on different virtual machines inside, on top of that hypervisor. That's the most straightforward approach. You have a statically partitioned hypervisor, and then you simply put your ASIL-B, QM, and ASIL-A applications on top of that. Additionally, you are most likely going to have what is called a safety island. A safety island is just a number of cores that are in the same SoC, but are running are completely independent and are running a different operating system, usually a real-time operating system. This safety island usually has some kind of control over the application's core, so it can even, in some cases, shut them down or monitor them, whatever. But then again, this is what the first thought the automotive industry got about how to virtualize things and consolidate things. Use virtualization, static partitioning, move the ECU firmware into software running on different virtual machines. But this is not what we wanted to do with CentOS AutoSD. With CentOS AutoSD, we wanted to seize the opportunity that the industry is changing and evolving, to instead of going with something that is purely static, go all the way to something that it will be way more dynamic and software-driven. So the idea is to not use virtualization at all, which is kind of a weird thing to see at KVM forum, but the original idea was to not use virtualization and to use containers instead. In this case, every ECU software will be running on an independent container. Isolation will be guaranteed by using container namespaces, C groups, and container technology. We all know about it. And we also are helping in the industry to move faster, which is another really huge concern by the industry right now, because there are newer companies that are able to, well, most of the industry was creating platforms with a 4 or 5 year cadence. There are newer companies that are moving at that 18 months cadence. So they are developing new car platforms every roughly 2 years, 1.5 years. So it's quite a difference. And by adopting the container approach, we are able to offer users the ability to, instead of develop to adopt all the container workflow and adopt all the container methodologies, to use CI/CDs that are already used for containers, to enable easier testing, easier developing, and so on. So we were happy about that. We were presenting this. Everyone was happy, instead it didn't work all the time. So, for instance, one of the biggest challenges we found is that popular API software, such as primarily Android Automotive OS, cannot be easily containerized. It's not that you can't containerize it, it's doable, but it's very, very inconvenient. Because, for instance, your host kernel needs to be extended to support that particular workload, and it also gives you a kind of a moving contact surface between the rest of the operating system and the IBI. So, of course, one easy way probably the best way to address this concern is to use virtualization. If you use virtualization, you have a well-known contact surface between your IBI and the rest of the operating system. Now, of course, what we thought about doing is putting Android Automotive OS into a VM. And to do that, we first need to acknowledge what are the requirements of Android Automotive OS. So first of all, I think it's important to clarify that Android Automotive OS and Android Auto are two completely different things. despite the very similar name. Android Auto is just this feature that some cars have that allows you to connect your phone and stream and have your control your phone directly from their IVI on the car. And Android Automotive OS actually is a full Android derivative operating system that is targeted towards the automotive industry. It's kind of interesting the fact that applications developed for Android Automotive OS they are developed using a framework that is built on top of the Android SDK. And this framework is targeted towards distraction prevention. So they force developers to build UIs that are not distracting to the driver. And also they are aware of the state of the car. So if you are parked, they can have more interactive UIs. If you are in movement, there are some restrictions about what you can put on the screen. And what's interesting and what's really nice for us is that the reference implementation targets actually a virtual platform. It was originally called Trot. Now, as far as I know, it's Cuttlefish Auto. So to be able to run Android Automotive OS, you need to support basically those Virtual devices. I don't think this list is actually really updated, even though I took this screenshot a couple of days ago. But, well, it gives you a rough idea of what you need. Some of them are easy, because some of them are VSOC-based, which basically means this is a software component that is communicating with another software component that is outside the VM. You also need Virtual Sound, which was not upstream until very recently. You also need Virtual Console for Bluetooth, because that's basically a serial device. If you want to have EBS, you need Virtual Media Video or Virtual Media, which is basically an interface for hardware coding and decoding. Of course, you need Virtual GPU, because if you have ever run Android without GPU acceleration, you'll know you are up for a bad time. And you also need Virtual CMI for sensors, but also in some cases for power management. And some vendors are exposing power management to SMI. And we also need Virtual Input, but with touchscreen support. And possibly some others that are not yet here, but mostly those are the most important ones. So when it comes to QEMU, well, the first thing we needed to do is to actually add multi-touch support to Virtual Input, which it didn't have before. And then we started thinking about how to bring and support some of the additional Virtual devices that we needed. And when thinking about that, we settled on favoring RAS implementation of out-of-process devices using vHost user. And we started contributing and developing to existing or creating new software, new of those vHost user devices, hosting them within the RAS VMM umbrella project. Some of them, such as vHost user CMI and vHost user sound, are already merged in upstream in RAS VMM. vHost user media is still in the works. So there are people in the team working, helping getting the specs ready, making a RAS implementation. And for vHost user GPU, which will you learn more about that tomorrow in Matej's and Dorinda's presentation, we decided, even though there was already a C implementation that is in the QEMU source code, we decided to, because it was a bit dated, we decided to pick up pieces from CrossVM and libkrun and spin out a different dedicated vHost user device implemented in RAS. And this one with GFS string support, which also we'll talk about it tomorrow. That is really important because Virtual is getting deprecated in Android Automotive OS. Now, the other thing we needed to do, in addition to have Virtual devices, is to have a way to consume the Android Automotive OS these images. So when you build the system with Android Automotive OS, what you get is basically this kind of files that are more targeted towards flashing them into some device. So we needed to transform them into something that could be easily consumed by QEMU. So we came up with a CVD2IMG, which basically does that job. It takes those images and produces raw images that then can be transformed into QCode2 or whatever you need. And it also embeds the device properties that are required by Android to actually boot the device. And to be able to start everything, because you need to start QEMU, but you also need to start a number of additional components, we came up with Start AVM that is basically a small script that sets all the stage and is container friendly because we wanted to run all of this inside a container. And in fact, that's what we did. We put everything into a container using Start AVM has the entry point. This container will need to leak some devices. For instance, we need def DRI for GPU acceleration, and we also need access to a secondary DBOS server. We run QEMU headless, so the SPIAD input is actually managed by a different component that is running in a different container, and it communicates with QEMU using DBOS. And this image may be part of the container or may be provided externally has in some other volumes. There is also the option of having them directly in raw storage and pass that raw storage directly to the container. The decision of when to put the images, it really depends on how the user is expecting to update and distribute Android Automotive OS updates. Now, with this new piece, then we have this picture, and everything seems to be fine now. So we can have the ECU software running in one container, another ECU software in a different container, and or IVI running in QEMU also within a container. So we get both the container isolation and the virtualization isolation. We have, as we said before, a well-known contact surface between the virtualization and the rest of the operating system. So everything looks fine. And in fact, this is where I should be ending these slides. Instead that, and this is a new development. Some months ago, we found that it's never that easy. So in certain markets, it turns out that using virtualization is pretty much a requirement. It's not like the regulation says you need to use virtualization for this particular component, but it's that everyone in that market, the auditors, the regulators, are used to see virtualization. So try, for at least for one particular component, so trying to go against the stream is very hard. So at least for the time, it's better to comply. So, but the problem here is that, okay, we should be able to virtualize that component too, but we didn't want to introduce a new development workflow. We didn't want to have a different way for creating VMs, for defining VMs or building VMs. So we put some requirements on this new way of introducing virtualization in CentOS AutoSD. So we wanted to preserve the container deployment and development workflow as much as possible. Everything should be everything should be done through Podman, and it should be compatible with quadlets. These images are not an option because a big part of what we are shipping with CentOS AutoSD is based or is driven by ComposeFS, FSVerity. Significant parts of the value propositions are based on that kind of having everything on a file system. We are also using sign files, sign containers, Delta updates. We will lose all of that if we're using these images. And also, startup time is extremely important. It's extremely important, 3 times extremely. If you don't get into the KPIs, into the startup KPIs, you are out of the game. It's game over. There is no, it doesn't matter anything else. So thinking about that, we came with this solution, which is using libkrun for doing the virtualization of small headless components in AutoSD. So for those who don't know it, libkrun is a small VMN written in Rust and provided as a dynamic library. It's already integrated in Podman using through crun. So by using a dynamic library with crun, we guaranteed smaller, we avoid the requirement of a shim, so we have a lower startup time, but we also make easier to switch between different namespaces since everything is loaded by dynamic loader the moment the crun is started. libkrun has an in-process virtualization support, so we don't need to use these images. I mean, this may sound like I'm contradicting myself because just before a couple of slides ago, I say that we prefer out-of-process because user devices. But in this particular case, startup is so important that it trumps anything else. So we actually need to favor this, having this kind of speed up. It's also, the fact that it's smaller is also makes it more, give us some kind of future-proofness for the future in case we need to adhere to some future requirements. And finally, this is how it actually looks. This is the final picture for AutoSD virtualization, approach to virtualization. So we have some ECU components running in containers. We have some ECU components running in containers with KRun. So they are actually virtualized using isolated using virtualization. And we finally have the IBI running in a container with QEMU and running under the Automotive OS. And I think that's basically it. So I hope you enjoyed and learned something interesting about the automotive industry and virtualization in this topic. And if are there any questions?
So about the devices, so what were the factors that you're favoring, like out-of-process devices using that VOC user interfaces? Is it the capability to work with other hypervisors or something else?
Mainly that is keeping the VMM small. So I mean, size and complexity, I can make functional safety requirements challenging, more challenging. So keeping everything small, and you know, you can get QEMU very small by using building it with modularity. It really favors the fact that we can use out-of-process devices.
Okay, thank you.
Hi. For the AOSP, why you use QEMU instead of cross VM? And do you consider other hypervisors? Why you choose PQEMU? Thanks.
Yeah, that's a really good question. We actually consider using cross VM for a while because cross VM was, of course, ready already to use Android Automotive OS instead of QEMU, which you need to evolve. The main reason basically is that our expertise is deeply rooted in QEMU. So it felt to us that we are kind of investing in the expertise we already had by using QEMU. Another reason is that CrossVM is not, it's an open source project, but I think in QEMU it's easier to make changes and suggest changes. So it's more open in some senses.
Do you get asked about the QEMU license requirements a lot from automotive vendors?
So far, no. So far, no, because the thing we've been doing with QEMU is that since we are offering as a container, it's kind of a self-isolated component. It's like users and partners may just need to provide the Android Automotive OS images, point it to them, and everything which ships like a kind of isolated component within the whole scheme of things.
So in your diagram, you had the application and RTOS safety island. Do you have any communication between the RTOS and any of the things running in your containers?
They can be through mailbox or yeah.
And is that a standardized thing or a specialized communication?
So far, we are not providing directly any support for that. So it depends on the BSP. Whatever the vendor provides is what we will need to adopt. It would be nice to have something standardized. We saw in the Linear Connect there were some ideas for that, and it would be really nice to have some queues standardized.
Virtualization backends.
Yeah.
Do you foresee any requirement for device assignment?
Any requirement, sorry, for?
For device assignment. So VFIO,
yes,
platform
yes,
pass-through? Or...
Yes, it's very likely that we are going to see the need to move VFIO device, use VFIO to delegate network, especially network devices, through VMs running there. And that's kind of a challenge because it's not, in most cases, it's not PCI. So those are platform devices that may require kind of mediated the drivers in the kernel to actually be able to play nice with VFIO. But yeah, that's something that we are seeing already.
Okay, we are out of time. Thank you.
Thank you.